Okay, let's unpack this. There's something really captivating, isn't there, about humanity's biggest ambitions? Building huge things, reshaping the world, sometimes doing what seems impossible. These massive projects, whether they're ancient wonders or modern marvels, they really grab our attention. And today, we're zeroing in on one of the biggest, maybe the biggest, most game-changing mega projects ever, the Panama Canal.
Oh, absolutely. And, these huge projects, they're so much more than just impressive construction. They're incredibly complex tapestries, really, woven from amazing vision, brilliant engineering, sheer political muscle, and just immense human effort, often stretching over generations. And the Panama Canal, it's maybe the ultimate example of all of that rolled into one, a true path between the seas, as McCullough calls it, that literally changed the map of the world.
So we're doing a deep dive today into a whole stack of sources. At first glance, they might seem kind of all over the place: old architectural books, biographies of engineers, modern project management guides, even stuff on urban planning. But they all connect back to this core theme. How do we dream up, plan, and actually build these massive world-changing things? Our mission today is to pull out the key insights, help you see the common threads, the why and the how behind these enormous constructions. And we'll be using David McCullough's incredible book, The Path Between the Seas, as a kind of anchor, guiding us through that epic struggle to build the Panama Canal.
Exactly. And as we go, you'll hopefully get a much deeper feel for how design, logistics, politics, and just sheer human will all interact, sometimes over centuries. You'll see the universal challenges that keep popping up. We'll really trace that incredible story of cutting a path between two oceans. Not just the amazing engineering, but also the really staggering human cost and the legacy of a project that truly did conquer nature in a way.
Okay, so building on that idea of ambition, what exactly is this vision we're talking about? Why is it so fundamental for these huge, long-term, incredibly expensive projects? Is it just about the size, or is there something more to it?
No, it's definitely more than just size. It's fascinating, actually. A clear project vision, like the ones described in modern project management texts, isn't just a slogan you put on a poster, right? It's the essential spark, the fuel that gets these monumental things going in the first place. The sources talk about it being the project's core purpose, a realistic, attractive picture of what you'll get at the end.
Realistic and attractive.
Okay. But for something like the Panama Canal, that vision had to be way more than that. It needed to be a kind of foundational belief system, something so powerful it could unite huge, diverse teams, keep the funding coming for decades, and inspire people to keep pushing through unbelievable hardship. Think about it. The vision was this strategically massive recalculation of global power, of global trade. It had to be magnetic enough to justify this unprecedented effort, this mobilization of resources and, tragically, human lives.
That's a really powerful way to put it. A vision that doesn't just guide, it almost demands to be made real. I'm thinking about Robert Moses in New York. Our sources mention his almost romantic passion for physical accomplishment, for beautifying the city. That personal drive led to huge public works. But the Panama Canal's vision, that seems like it was on a whole different level, wasn't it? It wasn't just about making a city nicer. It was about changing global geography.
Exactly. Moses's vision, huge as it was mostly civic, maybe driven by his own temperament, though it obviously had massive impact. The canal vision, that was a national goal, a geopolitical statement. The sheer audacity of it slicing a continent in two to link the world's biggest oceans. That's a vision that commands attention and crucially commands immense resources. That core idea, that compelling story, it acted like a compass through every single crisis, every setback. Without it, all those thousands of decisions, the millions of hours of work, the money, the lives lost, it would have just fallen apart. It lacked that cohesion.
Right. It kept everyone pulling in roughly the same direction, even when things got incredibly tough.
Precisely. It kept the focus clear when, inevitably, huge challenges came up. And its eventual completion became this massive symbol of human grit and ingenuity, even with that terrible human cost. So that vision, it had to be attractive, believable, and compelling enough for so many people, from presidents down to laborers, to commit to something so difficult for so long. The real insight here is how a truly powerful vision doesn't just set a goal, it kind of forges an identity. It fuels an epic struggle. Hashtag 1.2. Political will and overcoming systemic obstacles.
That kind of individual drive, that refusal to give up, it reminds me of Isambard Kingdom Brunel. Our sources quote his philosophy: sticking to the one point of attack, and if the force first brought up is not sufficient, to bring 10 times as much, but never to try back upon another. That's incredible tenacity. But how does that individual grit scale up? How does it translate into the political world, overcoming massive systemic hurdles on a national or even global stage?
Well, that's the crucial question, isn't it? How do you keep that drive going against, as the sources say, unforeseen difficulties, delay, and expenditure, and often huge opposition when it's not just one engineer building one ship, but an entire nation's focus? Brunel's idea captures the necessary persistence perfectly. For the Panama Canal, though, it wasn't just about engineering problems. It was a masterclass in logistics, project management, and crucially, sheer political will. Remember the French attempt? It was disastrous. And a huge part of that failure was the lack of sustained political backing, the inability to really, absolutely, the U.S. buying the French rights, the complex, let's say, assertive diplomacy with Colombia and then later Panama, and then the sheer scale of financial and military commitment. It showed a level of political will that was pretty much unprecedented. Theodore Roosevelt really embodied this. He saw the canal as vital, strategically essential, and just relentlessly drove it forward. He was living Brunel's maxim. Don't look for an easier path, just bring 10 times as much force, whether that meant political pressure, naval presence, or just pouring in money and resources.
It makes you think of Robert Moses again in that civic context. The sources describe him as a knife through bureaucracy. Somewhat people were afraid to cross because he'd kick you in the balls, apparently.
Yeah.
He was incredibly skilled at getting funding, like that $2 million for the West Side Drive, or using horse trading to get land for free.
Exactly. Moses showed how political skill, even kind of ruthless tactics, can cut through inertia to achieve big urban goals. You know how to work the system, how to secure funding, how to get property.
Now imagine applying that kind of relentless pressure, the strategic maneuvering, not just within a city, but on an international scale. Dealing with other countries, impossible terrain, deadly diseases. It really drives home that vision alone isn't enough. You need that stubborn, almost brutal will to make it happen, even when everyone's telling you it's impossible or actively trying to stop you.
That's the key takeaway. These monumental projects don't happen in a vacuum. They're embedded in complex political and social systems. To make something like the Panama Canal a reality, you needed leaders who not only had the vision, but also the capability and the ruthlessness, frankly, to dismantle or bypass the obstacles. They had to be ready to bring 10 times as much force, whether it was Brunel's hydraulic presses or America's diplomatic and financial might for the canal. The political ambition had to match the engineering dream. It was a long, hard fight, truly an epic struggle. Yeah. The insight is that political will isn't just saying yes to an idea. It's about forcing yes into existence through relentless calculated action against truly staggering odds.
Okay, so moving beyond the vision and the politics, let's get down to the actual, the physical stuff. It really sounds like job one is understanding your materials inside and out, like the very DNA of wood, the properties of concrete. It's all about what the material can do, right?
Yeah.
How fundamental is that?
Oh, it's absolutely fundamental. Not just step one. It's a timeless principle you just can't ignore. Architects, engineers, they have to have this deep, almost intimate knowledge of their materials. What are their inherent properties? You know, Viollet-le-Duc talked about expressing the properties by the forms we give to our materials. It's about respecting what wood is, its cell structure, its grain, its strength, or understanding concrete or steel. Think about wood framing. Our sources mention that just nailing joists to headers isn't enough for proper load transfer over time. You need things like sheet metal joist hangers to really do the job reliably. It seems small, but it's crucial.
That's a great example. A tiny metal bracket making all the difference. It highlights the depth of knowledge needed, even for basic things. But how does that scale up? How does that principle apply to something as unbelievably massive as the Panama Canal locks, lifting giant ships up and over a mountain range?
Well, think about a simple concrete stair first. It's not just a lump of concrete, right? Our sources describe it as an inclined, one-way reinforced slab, basically a mini bridge. How it carries load, how far it spans, how it's supported, it all needs careful engineering analysis. Now, take that same core principle, understanding exactly how each piece carries and transfers load, and scale it up monumentally to the colossal concrete lock chambers of the Panama Canal. Those structures hold back millions of gallons of water day after day, year after year. They withstand enormous hydrostatic pressure from the water and the ships themselves. The engineers had to have an unparalleled grasp of concrete. how it behaves in tropical climate, how steel reinforcement prevents cracking under immense stress. This deep material knowledge ensures stability, safety, and ultimately what you might call the truthfulness of the engineering, even if the architecture is purely functional, like a lock. The Panama Canal is just this epic showcase of material science pushed to its absolute limit at the time, especially with concrete and steel.
Right. And before you build up, you have to go down. Digging, preparing the ground, laying foundations. It's not just moving dirt around. It's a science, isn't it? Especially when you're dealing with tricky ground, unstable soil, lots of water. This is often where these huge projects hit their first massive wall. And nowhere more so, I imagine, than the Panama Canal.
Exactly. It really begs the question, how do you lay the foundation for something enormous when the Earth itself seems to be fighting you every step of the way? Even basic building codes, like our sources mention, emphasize things like damp-proofing, waterproofing, subsoil drainage. These hidden elements are critical. Now, imagine that on the scale of Panama, excavating the Culebra Cut. That wasn't just digging. It was this monumental, prolonged battle against landslides, unstable rock, torrential tropical rain. The sheer amount of earth they moved is mind-boggling, millions and millions of cubic yards. But it was the constant fight against erosion, against water infiltration made worse by the climate, that demanded this absolutely cutting-edge understanding of soil mechanics and how to manage water on an unprecedented scale.
It's a sobering thought. The biggest challenges are often literally buried. Soil mechanics and water management weren't just engineering problems for the canal, they were matters of life and death. Those requirements in the sources about dam-proofing and managing hydrostatic pressure, they take on a whole new, terrifying meaning when you think about the constant battle against water during the canal's construction. Water causing landslides, water breeding disease.
Absolutely. That detail about needing extra subsoil drainage when damp conditions hit below-grade rooms, if you don't manage that principle on a grand scale, it leads to catastrophe. The French, when they tried for a sea-level canal, tragically underestimated these geological and hydrological challenges, especially in the Culebra Cut. And critically, they underestimated the waterborne diseases. The human cost, we talked about those tens of thousands of lives lost to accidents and diseases like malaria and yellow fever. It directly highlights this deadly struggle with nature in the tropics. Managing water was inseparable from managing disease. Stagnant water meant mosquitoes, which meant yellow fever and malaria, which devastated the workforce.
So the Americans learned from that tragedy.
They had to. They realized that controlling water, both in the ground and on the surface, and dealing with the health consequences, was just as critical as designing the locks. Conquering the ground meant conquering disease, too. It was this holistic approach. Understanding the environment was hostile. The ground wasn't just a place to build on. It was a battleground against geology, weather, and microscopic killers. Hashtag 2.3. Designing for function, aesthetics, and brutality.
Okay, let's shift to design itself. There's often this tension, right, between pure function, just making something work, and artistic vision, making it beautiful. Do you build a functional box, or does the structure itself become the art? Seems like different eras, different architects have different answers. Our sources mention how architectural programs, the purpose and form of buildings, change based on needs, climate, customs, taste.
Yeah, and tracing that evolution is fascinating. Viol-le-Duc pointed out how Greek architectural orders weren't just decoration, they were the structure, a direct expression of how they built. Then you look at the Romans, who often took those same Greek orders and just applied them like wallpaper, separating the look from the underlying structure. Fast forward to someone like Palladio. He's meticulously designing villas like the one at Bagnolo, thinking about function and aesthetics where the master lives, specific room heights, carefully placed stairs, balancing different elements. Then leap again to Le Corbusier, dreaming of factory-made houses, concrete frames focused on hygiene, clear function, stripping away ornament. And then you get to New Brutalism, which goes all in on formal legibility of plan, clear exhibition of structure, and valuation of materials for their inherent qualities as found. Think Louis Kahn's Yale Art Center, raw, honest, almost celebrating its construction. Each approach is chasing a kind of truth, serving the needs of its time.
That's a really interesting journey from structure as decoration to decoration separate from structure, back to a very raw, honest display of structure and materials. How does that idea of an architectural program even apply to something like the Panama Canal? It's pure function, isn't it? No columns, no fancy facades.
You could argue the Panama Canal is the ultimate expression of pure function, almost a kind of engineering brutalism, if you stretch the term a bit. Its design, though not architectural in the usual sense, was totally driven by one thing: Moving ships efficiently, reliably, safely, the colossal locks, the deep cuts like Culebra, the massive dams, they embody this raw, unadorned utility. The sheer scale of the task dictates the form, and there's a kind of stark, powerful beauty in that, isn't there? It's an incredibly honest expression of its purpose. It is a machine for global shipping writ large. That idea from brutalism, formal legibility of plan, clear exhibition of structure, you can kind of see it in the canal, those immense concrete structures exposed to the elements, they are brutally honest about what they are and what they do. They don't hide behind anything. They are the function. That focus on inherent qualities of materials resonates too. The ingenious lock system, as McCullough calls it, wasn't designed for looks. It was designed for the precise, efficient movement of ships. The insight, maybe, is that monumental design, even stripped of all traditional aesthetics, can achieve its own kind of profound truthfulness through absolute dedication to its core function. Hashtag tag 2.4. Innovation in digital integration in modern construction.
Okay, so function dictates form in something like the canal. But thinking about how things are built now, wow, we've come a long way from just physical drawings and models, haven't we? Digital tools seem to be everywhere in complex construction. Our sources talk about BIM building information modeling, doing detailing, specs, cost estimates. What does that actually let engineers and builders do now that was, well, impossible back then?
Oh, it's a complete game changer. Modern megaprojects are often built virtually, multiple times, before anyone breaks ground. BIM is central to that. It allows for these really collaborative processes like design build or integrated project delivery, where everyone, architects, engineers, contractors, works within the same digital model. It breaks down silos, and the capabilities are incredible. Things like clash detection. The computer automatically finds where, say, a pipe is modeled to go through the same space as a steel beam. You find that conflict in the model, not when the pipe fitter shows up on site and can't install the pipe. There's an example in the sources about the Yas Island project in Abu Dhabi. They used BIM to model the actual space welders would need to work safely. Clash detection identified potential hazards where different teams might interfere with each other. They solved safety issues virtually, proactively.
Wow. Fixing safety problems before they even happen. That's huge.
Yeah.
You also mentioned 4D and 5D BIM. What's that about?
Right. So 4D basically links the 3D model to the construction schedule. You can create these animated sequences showing how the project is planned to be built over time. It's incredibly powerful for visualizing the construction sequence, finding potential bottlenecks in the workflow, coordinating deliveries, and even running what-if scenarios to optimize the schedule. You literally watch the building come together on screen. And 5D adds cost to the mix. Every element in the BIM model, every beam, every pipe, every wall can have cost data attached. So you get much more accurate cost estimates updated in real time. You can see the cost implications of design changes almost instantly, which helps with value engineering. It's just a massive leap in managing logistics, cost, and schedule compared to, the era of the Panama Canal. A lot of the errors, the clashes, the iterative design refinements happen in the computer now, saving huge amounts of time and money and reducing risk on site.
It really makes you stop and think, how on earth did they manage the Panama Canal without any of this? Coordinating hundreds of thousands of workers, massive amounts of materials, incredibly complex digging and building sequences, all without a shared digital model or clash detection.
It's almost unbelievable, isn't it? It just underscores the sheer human ingenuity involved back then. They relied on incredibly detailed paper plans, physical models, constant on-site supervision, communication, and just relentless problem solving. The lack of BIM meant every potential clash, every scheduling issue, every design tweak had to be figured out the hard way through physical trial and error, intense supervision, and, sadly, often through costly mistakes, delays, and accidents. The immense risks McCullough talks about were magnified because they didn't have these tools to resolve it ahead of time. It shows how relatively primitive construction management was then, making the canal's completion a real testament to a different kind of intelligence, human-driven adaptation and innovation, rather than digital precision. Human ingenuity was the expert system back then.
Okay, project management basics, time, cost, scope, quality. We get that. But scaling that up, coordinating hundreds of thousands of people, millions of tons of stuff, literally battling a continent for the Panama Canal. What did control even look like back then? How do they manage that chaos?
That's the million-dollar question, isn't it? How do you manage that level of complexity without it just collapsing into total chaos, especially when you're fighting geology and disease at the same time? Modern project management relies heavily on techniques like the critical path method, CPM. Basically, you identify the sequence of tasks that absolutely have to finish on time for the whole project to finish on time. That's the critical path. Any delay on a critical path activity delays the whole project. Other tasks might have some float or slack, but those critical ones are non-negotiable. Our sources point out how one critical task slipping can push the entire completion date back. It ties directly into that bottleneck idea for manufacturing. An hour lost at a bottleneck is an hour lost for the entire system. Focusing effort on non-critical tasks might feel productive, but it's a mirage if it doesn't help the critical path move faster.
Right, so pinpointing those critical tasks, those bottlenecks, is everything. For the Panama Canal, with logistics spanning the globe, that kind of scheduling, even if they didn't call it CPM, must have been incredibly intense. What were some of their major bottlenecks?
Oh, the canal was just a series of massive shifting bottlenecks. The Culebra Cut excavation was the most obvious. The sheer volume, the constant landslides, that was a huge one. But also building the enormous lock gates, getting them fabricated and transported. The supply lines for everything cement, steel, coal for the steam shovels stretching across oceans. And maybe the most critical bottleneck of all, the health and availability of the workforce. Disease could shut down operations faster than almost anything else. They had to coordinate materials, equipment, tens of thousands of workers. They needed sophisticated scheduling, even if it was done with charts and graphs on paper. Dynamiting, digging, pouring concrete, laying railroad tracks to haul away, spoil it all had to be sequenced. The critical path would have been a constantly moving target, disrupted by landslides, floods, equipment breakdowns, disease outbreaks. Their ability to react, to adapt, to resequence work on the fly must have been extraordinary. It shows this incredible human capacity for dynamic control under pressure. That epic struggle McCullough describes was as much about mastering scheduling and logistics as it was about the physical digging and building. Managing that complexity meant constantly finding and breaking bottlenecks to keep things moving forward. Hashtag TAC 3.2. Risk management and quality assurance.
And building something that big is just inherently risky, sometimes catastrophically so, as the French discovered in Panama. So how do you manage that? How do you minimize the chance of disaster, both in planning and during construction, and make sure the thing actually works reliably in the end?
Yeah, risk is unavoidable in projects like this. The key, as our sources suggest, is managing it systematically, starting right from the beginning. It's not about eliminating risk that's often impossible, but about identifying potential problems, understanding their likelihood and impact, deciding what to do about them proactively. For the Panama Canal, the immense risks were just staggering. The French failure is the ultimate case study in unmanaged risk. They failed to grapple with the engineering risks, the geology of the cut, the flawed sea level design, and crucially, the catastrophic risk of disease. They literally risked and lost tens of thousands of workers.
That difference between the French and American approaches to risk is just night and day, isn't it? The French seemed overwhelmed by risk they didn't foresee or couldn't control, especially disease. But the Americans seemed to make risk management, particularly medical risk management, a core part of the whole strategy.
Absolutely. The American effort, led by figures like Colonel Gorgas on the medical side, was revolutionary in how it tackled risk. Those medical breakthroughs in sanitation and mosquito control weren't just scientific side projects. They were treated as critical engineering problems, as essential risk mitigation strategies. It was a massive example of identifying a huge risk disease decimating the workforce and throwing enormous resources and scientific effort at mitigating it. You could even see the U.S. government taking over as a form of risk escalation, bringing national-level resources to bear on problems the French couldn't solve. And alongside risk management, you need quality management, ensuring that what gets built actually meets the standards and will function reliably. In modern projects, you have things like project management offices, PMOs, overseeing quality, and construction managers monitoring contractor work, arranging tests, making sure specifications are met. For the canal, quality assurance wasn't just about the concrete mix or the lock mechanisms. It extended to the environment itself, making the work zone healthy enough for people to actually survive and work effectively. That was a fundamental quality requirement. Those immense risks and rewards of nation-building infrastructure were totally dependent on the ability to manage risk effectively. The insight is clear. For huge undertakings, systematic risk management isn't just good practice. It's often the deciding factor between failure and success.
These huge projects are inspiring, no doubt, but they often have this darker side, this immense human cost. Especially looking back historically, it really makes you appreciate how vital safety is in construction today.
It absolutely does. And it forces that difficult question, what is the acceptable cost of progress? Especially when the ambition is so vast. Historically, The human toll could be just horrific, and the Panama Canal is one of the most tragic examples. McCullough documents those tens of thousands of lives lost to accidents and diseases. That wasn't just a statistic. It was a fundamental, brutal cost of achieving that vision. It's interesting how our understanding of accidents has evolved. Early models, like Heinrich's domino theory, have shifted towards emphasizing management's responsibility for creating safe conditions. That lens really changes how we view the history of projects like the canal.
It's such a stark contrast, isn't it? This incredible feat of engineering standing alongside this immense human tragedy. Those medical breakthroughs weren't just abstract science. They were desperate measures to stop the dying, to make the project physically possible to complete. It really underscores how the human element is both the engine and most vulnerable part of these massive efforts.
Exactly. While the understanding of disease was incomplete during the French attempt, the American success showed this huge shift. Prioritizing worker health became essential, driven by necessity and a willingness to invest massively in sanitation and mosquito control, those medical breakthroughs. Modern safety is incredibly rigorous by comparison. We have job hazard analyses, JHAs, for risky tasks, mandatory safety meetings, constant monitoring by construction managers, written notifications of hazards. The scale of loss on the canal really highlights why these modern protocols are so critical. We even see pre-qualification of suppliers based on safety records now. And thinking about technology, those expert systems designed to transfer skill from employee to employer. They raise questions about the future of work and skill. The canal predates all that, of course. Managing that vast, vulnerable workforce without modern safety science or digital tools was an immense ethical and logistical challenge. The real insight is that while we celebrate the achievement, the true measure includes acknowledging the human cost. What was built, yes, but also at what price? Hashtag 4.2, long-term impact and adaptability.
And once these things are built, they don't just sit there, do they? They take on a life of their own. They shape the environment and how people live. And sometimes the original plan kind of morphs into something else entirely. Our sources talk about buildings being like living things, alive and evolving, maybe even improving if given the chance. And the idea that buildings should invite adaptation because function changes over time.
Yeah, that's a really important point. A monumental project is never truly finished. It becomes part of a bigger system and keeps evolving, often in ways the original builders never imagined. Robert Moses's parkways are a good example. The sources mention Riverside Park in New York, built to reclaim the city's waterfront for its people, a great vision. But the parkway itself often ran closest to the river, physically separating people in the park from the water they came to see. An unintended consequence, a complex legacy where the outcome didn't quite match the initial promise of connection.
That's fascinating, the unintended social impact. The Panama Canal's long-term impact is even bigger, more global, isn't it? It didn't just change New York, it changed the world map. Global trade, naval power, forever.
Absolutely. The canal's completion in 1914 wasn't just about shorter shipping times. It fundamentally reshaped geopolitics, global economics, military strategy for over a century now. It wasn't designed to adapt like a building might get renovated, but the fact it's still operating still crucial despite massive changes in ship sizes, global politics, technology. That speaks volumes about the robustness of its core design. It has an inherent, if somewhat rigid, adaptability. Even simple design choices reflect this long-term view, like pitched roofs versus flat roofs. The source notes pitched roofs are generally better long-term for shedding water and dealing with heat, while flat roofs often develop hard-to-fix leaks. Small decision, big long-term impact. The canal's legacy is incredibly complex. McCullough's narrative highlights this tension. It conquered nature but was built on a foundation of immense human sacrifice. Evaluating its true success means looking at its enduring function and its lasting social, human, and environmental consequences, both good and bad. It's a powerful reminder that the story doesn't end when the ribbon is cut. Hashtag 4.3. The philosophy of engineering and systems thinking.
Beyond the concrete and steel, there seems to be something deeply satisfying about engineering, about shaping the physical world, and also a deep intellectual challenge in figuring out how all the pieces fit together. Our sources mention the existential pleasure of engineering this immersion in the material world, even in the mundane tasks. How does that relate to projects on the scale of the canal?
That idea of existential pleasure is really interesting. It's not just about the final grand result, but the satisfaction found in the process, in the problem solving, in engaging directly with the material world, even the mundane activities. And this ties beautifully into systems thinking, realizing that the world, and especially a huge project, isn't just a collection of separate parts, but a web of interconnected stocks and flows. The sources point out that it's easier to learn about a system's elements than about its interconnections, but understanding those connections is crucial. You can't really control complex systems perfectly, but you can understand them better, and you can design and redesign them. You learn from the surprises. That whole cycle of learning and adapting is absolutely central to any monumental effort.
That idea that systems can't be controlled but they can be designed and redesigned feels incredibly relevant to the Panama Canal. It must have felt utterly uncontrollable at times. How did they apply that kind of thinking?
Well, they had to, didn't they? The canal wasn't just a construction site, it was this dynamic, unpredictable, often dangerous system. The engineers learned very quickly that digging the Culebra Cut wasn't separate from managing the water levels behind the Gatun Dam, which wasn't separate from controlling mosquito populations to keep workers healthy, which wasn't separate from managing global supply lines and political pressures. It was all interconnected. They couldn't control the geology of the cut, or the rainfall, or the biology of the mosquito perfectly. But by understanding how a landslide in the cut affected everything, downstream spoil removal, worker morale, disease vectors, they could design and redesign their approach. They learned from every setback, every surprise, to keep the whole massive system moving forward. It meant constantly adapting. Landslides bigger than predicted. Redesign the slope, change excavation methods, yellow fever outbreak. Double down on sanitation, screen windows, drain swamps. It was continuous learning and adaptation. The sources say the future can't be predicted, but it can be envisioned and brought lovingly into being. That iterative process, expecting the unexpected and learning from it, was absolutely vital. That is, systems thinking in action, maybe in its most raw and high-stakes form, and overcoming those challenges, wrestling that complex system into existence, bringing lovingly into being that vision against all odds. That captures the profound intellectual challenge and, yes, the existential pleasure engineering can offer, even amidst tragedy and struggle. #tag outro.
So we've journeyed through this incredible world of monumental undertakings, from the huge visions that kicked them off through the real nuts and bolts of engineering, the complex dance of project management, all the way to their lasting impact, their legacy. And the Panama Canal really stands out as this powerful, maybe sometimes uncomfortable example of all those layers: human ambition, ingenuity, cost, and consequence, all rolled into one.
Yeah, we've seen that success isn't just about building the thing itself. It's about the clarity of the initial vision, the absolutely unbending will of the leaders involved, the rigorous, detailed application of science and engineering, and the tools, whether rudimentary or digital, used for collaboration and managing risk. And maybe most importantly, it's about acknowledging the human story. The stories of incredible ingenuity, yes, but also the stories of immense sacrifice that underpin these massive achievements. They don't just shape the land, they shape societies, as the canal story makes so incredibly clear in both tragic and triumphant ways.
So next time you see a massive bridge, or a really old impressive building, or even just a complex construction site humming along, maybe take a second. Think beyond the physical structure. Think about that invisible architecture underneath the vision, the persistence, the raw human ingenuity, and maybe the human cost that brought it into being. What stories are hidden just beneath the surface, like the ones embedded in the earth and concrete of the Panama Canal?
And maybe ask yourself this: how many of the big structures you see or use every day reflect this kind of deliberate mix of principles? Especially, how did they factor in the human element, the workers, the communities affected? What values, what assumptions about risk, cost, and progress are built right into their design? What does that tell us about the time they were built? Often the answers are right there, hiding in plain sight, just waiting for your own deep dive.